This is a word problem that has to do with related rates. And it says a boat is being pulled into a dock by a rope attached to the bow of the boat, passing through a pulley on the dock which is 1 meter higher than the bow of the boat. If the rope is pulled at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? Okay, the situation that we're dealing with here is going to set us up with a right triangle. So we'll visualize this right triangle with the rope, the dock, and the boat, like so. Okay, I'm going to label my sides X, Y, and Z, but any letters will do in this instance. This will be the dock over here, and it tells us that it's 1 meter high. This will be the rope over here, and then over on this point would be the bow of the boat. Okay, so what we're dealing with here are rates of change and the lengths of the sides of this right triangle. So dx over dt is the rate of change of x with respect to time. And that's how fast the boat is moving, and that's what we're trying to determine here. dy over dt is the rate of change of y with respect to time. But that's the height of the dock, which is not moving, so it's constant, and its rate of change is just a 0. dz over dt will refer to the rate of change of the rope with respect to time. It tells us in the problem that that's 1 meter per second. Okay, so now those are how we're going to interpret the rates of change in terms of our derivative notation. Now what else we know is that we're dealing with the moment at which the boat is 8 meters away from the dock. Alright, so now we'll put this together. The first thing to do is use the Pythagorean theorem, x squared plus y squared equals z squared. So we have numbers for x and y, in this case 8 squared plus 1 squared equals z squared. We're going to go ahead and put those numbers in and solve for how long z is. So that would be 64 plus 1 equals z squared, or z squared is 65. Z is the square root of 65. Okay, so now we have x is equal to 8, y is equal to 1, and z is equal to the square root 65. What we're going to do is again use the x squared plus y squared equals z squared formula, but this time we're going to take the derivative of both sides with respect to time. And that's going to introduce the derivatives and rates of change to our equation. So take the derivative of each term here. The derivative of x squared is 2x, but since we're taking it with respect to time, we have to put dx dt along with it. So it would look like 2x dx dt. The derivative with respect to t of y squared would be 2y dy dt. And that's equal to derivative of z squared would be 2z dz dt. And now we have this equation here. All the numbers above we can plug in to figure out what the unknowns are. So for x, we're going to plug in 8. For y, we're going to plug in 1. For dy dt, we're going to put a 0. For z, square root 65. And for dz dt, 1. So that would look like 2 times 8 dx dt plus 2 times 1 times 0 equals 2 times the square root of 65 times 1. And this would be then, let's see, 16 dx dt. This is all 0, and that's equal to 2 square root of 65. We'll divide each side by 16. That gives us dx dt. This reduces down to be just the square root of 65 over 8. And if we approximate that to 2 decimal places, it would be 1.01 meters per second. And then that represents the rate of change of x, or in this case, how fast the boat is traveling as it approaches the dock.